значение это не связано с какой-то частотой?
Ну, есть каналы, значит, и есть громкость.
Я вроде запустил, не удалось. Вроде работает.
Картинка есть.
Да, картинка есть, хорошо, звук. По фазе, да?
Да.
Сейчас, может быть, проблема с микрофоном, где...
Нет, скорее всего, это просто звук идет откуда-то из камеры.
Микрофон? Вот и должно быть нет. Сейчас я подключу звук-то. Сейчас звук в камеру подключу сюда.
Может быть, свой устройство фиксировано?
Ну, в принципе, наверное, лишнего не будет.
Значит, у нас проблема со звуком.
Третий?
То есть ничего нет. Есть еще синк, есть соскал.
Сегодня я говорил алгоритм, звук берет, звук, нет, у меня отсутствует, он где-то, то есть, может, я с микрофона, откуда-то еще. Может быть, опять же, или
Состояние громкости, может увеличиться, наставление канал, почему микрофон, соответственно,
ну, может быть, он передает, но где-то промежутки,
Так, сейчас, подождите.
Да, хорошо. Да, хорошо, спасибо большое. Так, вот. Так, ну здесь какие-то есть установки, значит, банк 1, значит, канал 3. Значит, что это значит, неизвестно. Так, давайте вот так вот. 1, 2, 3. Вот так вот, значит, вот 1, 2, 3. Да, вот, да, вроде окей. Так, хорошо. Сейчас я позвоню Екатерине, скажу, что все вроде заработало. Да, Екатерина, у нас вроде все заработало. Да, спасибо большое. До свидания. Okay, well, let's begin. Okay, today I would like to describe a few examples of the cohomology of elliptic complexes. Now, let's recall what an elliptic complex is.
Well, an elliptic complex is a complex all differentials are all groups in the complex are spaces of sections of some vector bundles. Well, let's not assume that the manifold is orientable, although we'll need to do this soon enough. Anyway, we have a number of a collection of vector bundles over X, where X is compact and without boundary. And we also assume that the sequence of the symbols is exact, which makes sense because the order is the same. Okay, now in particular, it makes sense to consider the cohomology groups of this complex, and we saw last time that every cohomology class has a unique representative, has a unique harmonic representative. What does it mean? Well, it means the representative belongs to the kernel of the Laplacian operator. And in particular, if we assume the two theorems we saw last time about elliptic operators in general, then we obtain that all these spaces are finite dimensional, which is already something, because those vector spaces clearly aren't. And the Euler characteristic the Euler characteristic of this complex is equal the index of d plus, where d plus is the even part of this operator. What does this mean? Well, this means we have an operator. And this operator takes even elements to odd elements and vice versa, and the operator d plus d star is self-adjoint. So the index of this operator is not very interesting. But if we restrict the operator to the even or odd spaces, we get something more interesting, and the index is meaningful. Namely, it is the Euler characteristic. Now, let's look at this formula. This formula follows from what we saw last time, but last time I didn't mention this formula explicitly. So let's see whether the formula makes sense, and whether everyone understands where it comes from. Okay, so d plus and d minus are the adjoints of each other. Does this make sense? Basically, we use the fact that d plus d minus is d is self-adjoint, and then we take d plus d minus and apply the result to omega naught plus omega 1. And then omega naught plus omega 1. Okay, omega naught is an even form. Omega 1 is an odd form. Well, I write this scalar product, and then I use the fact that d plus d minus is self-adjoint, and what happens when I take this? When I take this this expression, well, d minus applied to omega naught is 0. Same for this product, and then I get a sum of two terms, and anyway, I don't want to write the details. We saw a similar formula a few weeks ago. Okay, so the first thing to notice is that one of the operators is the adjoint of the other, and vice versa, of course, and the So the index of the operator is the kernel is the dimension of the kernel of the operator minus the dimension of the kernel of the adjoint operator. What is the kernel of this operator? Well, as we saw last time, the kernel is the kernel is well, the kernel of D is the direct sum of its intersections with the individual homogeneous components, and so D plus and D minus interchange the odd and even components. So the kernel of D plus is the direct sum of the kernels of D for all even components. So the kernel of D plus is isomorphic or the same as the degree I component of the kernel of D, but we only consider even I here. And for D minus we get the same result, but for odd I, and so the end result is we need to take the dimension of the kernel of this minus the dimension of the kernel of this, which is precisely the Euler characteristic. Does everyone agree? This will be important in a minute, because we will now consider a few examples of elliptic complexes, and in these examples the Euler characteristic will be something well, in some examples it's just the usual Euler characteristic of X as a topological space, but in some other examples we get something more interesting.
There was a theorem, I guess it was called Hope-Quantum theorem, was determining the coefficients of a manifold with the index on vector field. How can you turn that theorem to this? Like, the coefficient of a manifold is the sum of the index of
well, indirectly, yes, but I don't know if there is a direct way to construct an elliptic operator starting from a vector field. A vector field is an operator. It operates on functions, and then by the way, what's the symbol of this operator? If we consider vector field as an operator, then what is the symbol?
just the taking differential, the equation of the vector.
Well, let's see. The symbol must do something with. Let's erase this part. Okay, the symbol is a map from the fiber of one vector bundle to the fiber of the other vector bundle, and this map also depends on an element psi, where psi is inside the cotangent bundle. Now, suppose I take EF both trivial, and I take a vector field as an operator. Now, the order is 1. So, what is the one symbol of this operator? Well, in this case, EX and FX are just R. And a map from R to R is multiplication by some number. Now, what is this number?
Maybe it's a product of given vector field at this point. Right?
Yes, well, exactly. So we just take the standard pairing between vectors and covectors, and this will be just the multiplication map by this number. Okay. Now it follows from this that if V has zeros, the operator is not elliptic. So there is no straightforward connection between this index and the index of a vector field. Okay. Now
But if it doesn't have zero, then we can apply this, right?
well, if it doesn't have zeros, then well, we get then we get an elliptic operator, and the
Its kernel is just the constant functions.
Yes, the kernel constant functions, and the well, I don't know whether the index of the resulting operator is has a nice meaning. Maybe it does. Well, let's think about it. In the meantime, let's move on to other examples. Well, the in in this case, the harmonic elements are precisely the harmonic forms in the usual sense, and there is and what we get is an isomorphism between harmonic forms and the cohomology of X with R with coefficients in R. Now, what else? And the Euler characteristic is the usual Euler characteristic. This is the classical de Rham complex, and there are, as you probably imagine, there are simpler ways of calculating the Euler characteristic than using the index theory. In itself, the de Rham complex isn't particularly interesting. But let's consider some variants of it. Let's in particular consider the Dolbeault complex. Okay, let's recall first of all what we did a few weeks ago, or maybe a month ago. So to begin with, let's assume that X is a complex manifold. Let me briefly recall that complex analytic means there is an atlas such that all charts take value in some complex vector space, and all transition maps are complex analytic. Or, in other words, they can be written as local at each point, as a power series that converges in some neighborhood of the point. An equivalent definition goes by the Cauchy-Riemann condition, and one can prove that if we have a function that satisfies the Cauchy-Riemann and is of class C1, then this function is in fact complex analytic, which is a remarkable result if you think about it. So we have a function which is barely differentiable, And then we require that this function should satisfy some differential equation, and it turns out that it's infinitely differential. Okay. Anyway, complex analytic manifold. Is everyone happy with the hand waving explanation I've just given, or do I need to write something on the blackboard? Okay. Now. Okay, let's let's briefly recall what we already saw a few weeks ago. So I consider the tangent or cotangent vector bundle and the exterior algebra of it, and here I consider them as real vector bundles. Now the result is the same as the result is the same as what we get if we first complexify, then take the exterior algebra, and then here I again consider this space as a real vector space, because otherwise nothing happens. Okay, now recall that if I take a complex vector space and then complexify it again, the result is isomorphic to the space plus the dual space, so I get this isomorphism, and then well, I can write the following thing. So, okay, let me take lambda n is isomorphic to sum of over p plus q equals n, lambda p q, where lambda p q is lambda p of t star x tensor lambda q of ts.
But he starts x on the tx, it is an indication when Hermitian metric is fixed.
No. Actually, what I've said so far makes sense for X, an almost complex manifold. I haven't really used the fact that we have a complex structure. So far, we only need an almost complex structure. But we'll shortly see where the complex structure comes in. So far, I have just this decomposition of vector bundles, and basically, to have it, I only need a complex structure on each of these spaces individually. And I need it to vary smoothly from point to point, which is the same as to say that we have an almost complex structure.
Well, my question was about the decomposition of T star X tensored with C.
Yes, for this, yes, for this decomposition, we need a complex structure on each fiber individually, but we don't need a metric. How do we get this decomposition? Suppose I have just a vector space, a complex vector space, finite dimensional.
I know these are just the eigenspaces of the complex structure.
Yes.
But why one of it is, why they are dual to each other? What is the pairing?
I don't know. Does anyone know?
But then they are not canonically dual.
Well, let's think. So we want to know. So V. Okay, so we want to decompose we want to decompose the vector space as V plus V dual. Okay. And more precisely, we want to know whether or not this involves a metric of some type on V.
Yes.
Well, if we have a metric on V, there's always a way to identify V with its dual. So in a sense that it's we don't need this. Okay, let's see.
This decomposition is like holomorphic tangent bundle and anti-holomorphic.
What is anti-holomorphic? That's precisely what we're trying to figure out.
Holomorphic means that the space where with the eigenvalue minus I of the complex structure.
Okay, so here's what happens. We have this decomposition, and let's look at it. both, okay, let's, instead of dual, let's write V10 plus V01. Okay, so we want to construct an isomorphism between each of these and V. How do we do this? Well. Let's see what happens. Let me tell you what I think happens. There is an isomorphism between V and V10 and a natural anti-isomorphism between V and V01. And then you probably want to use a metric to identify the vector space with the opposite complex structure with the dual space. That's probably okay. Let's think about it 3 minutes and then carry on. Okay, what's okay. Okay, probably like this. So when I complexify, capital I becomes just another operator. This operator squares to -1. Now, what if I take minus? Well, let's see. I want to have eigenvalue I. I apply this. I get I x. Okay. Let's see. So I x minus I x. What do I get? I get Алло? Да, алло. Добрый день, Алена. Алена, сейчас нет, извините, нет возможности. Sorry about that. Okay. Anyway, let's see. So we have ix plus ix, and this is the same as ix minus ix. Okay. Yeah, sort of works. And this is the same with the plus. Okay, so what do we have? We have this decomposition, and now, well, from this decomposition, we get a natural isomorphism. We take an x, and we send it to x minus blah blah blah. Now, is this isomorphism complex linear? Well, let's see. Okay, now Ix go to Ix minus I, so plus Ix, and what is this? This is Ix. Plus I, no, okay, so multiplication by capital I, hold on, no, this doesn't make sense, let's erase all this, no. No, it does make sense. Okay, Ix minus plus Ix, which is I X minus Ix. Does it work? Yes, yes, it does work. Okay, so so let's see. So we have Ix, which goes to Ix minus Ix. So this map is complex linear. And the similar map for the other component is antilinear. So the part we're able to do without the metric is this decomposition. Something plus something with the opposite complex structure, and then we could use a Hermitian metric to identify this thing with the dual. Okay, does this make sense? Yes, well, let's say complex let's say we have a Hermitian metric. But in any case, we have a decomposition on the level of vector bundles, so we need the Hermitian. No, sorry. Yes, we need the Hermitian condition for this equality. But we do have this decomposition regardless of whether or not we have a Hermitian metric. We need the metric only to identify the PQ component with with some power of t upper star and tensor some power of t without upper star.
Maybe in complex case, do we always have geometry like real case because I guess we don't have.
Yes, and for the same reason. And by the way, what is the reason?
The partition because it means it's not another.
Well, yes, but there is another ingredient. The set of all Euclidean metrics on a vector space is convex, and same for Hermitian metrics, and this is why the partition of unity works. Okay. Anyway, we have this decomposition now. What is the Dolbeau operator? We have the de Rham differential. We can complexify the de Rham differential. And then we can take this decomposition. And we can take the restriction of the de Rham operator, and then project onto apply it to a section of lambda pq, and then project to lambda p plus 1q. And similar with the other projection, and in general, if we have an almost complex manifold, these will not square to 0, and in fact. One of the many equivalent ways to say that the complex structure is the almost complex structure is integrable, is to say that d bar or d squares to 0. And okay, now there is a reason d bar is slightly more interesting than d. And the reason is this: the kernel of d bar the kernel of d bar in degree, the kernel of d bar in by degree p0 is precisely holomorphic p forms. And the kernel in degree 0 is precisely holomorphic functions. Now, we want to generalize this to arbitrary holomorphic bundles. Why? Well, because we want to calculate the cohomology of holomorphic bundles. Now, does the expression a holomorphic bundle make any sense? Володя. В общем, все то же самое, что в топологическом случае, только значит, все, что может быть голоморфно, голоморфно. Okay, now suppose we have x as above. And suppose we have a holomorphic vector bundle. I want to define an operator Okay, here I don't write an x, but obviously those lambda pq have been constructed starting from the cotangent bundle of x.
There we have PQ forms, but here we have only 0 Q forms. Is it possible to define d bar
yes, but then
I think we can just apply this construction to E equal to E not vector bundle tensor by vector bundle homomorphic.
tensor some exterior power of the holomorphic tangent bundle,
Yeah.
or cotangent bundle, probably cotangent bundle. We will shortly see why I take 0 here and why I'm not very interested in having an arbitrary p. What I want to construct is a fine resolution of E. Okay. Now to see what happens, let's. Okay. Let's recall a few things about sheaves. First of all, does the word sheaf make any sense? Sheaves have cohomology. Does the expression sheaf cohomology make any sense? Okay, very briefly. If I have a sheaf of abelian groups, I can take sections. But this this is this is something which is interesting but badly behaved. For example, if I replace a sheaf with a quasi-isomorphic complex of sheaves, the sections may change. And the idea is to replace sections with something which is easier to calculate, and which contains sections as a particular case. And this something is sheaf cohomology if one is just interested in so suppose I have a sheaf I replace this sheaf with and I want to calculate or to define its cohomology. I replace this sheaf with a gamma acyclic resolution. What does this mean exactly? This means I have an exact sequence of sheaves which starts with S and then goes possibly to infinity, and all individual sheaves here must be gamma acyclic. Which means the higher cohomology of each individual sheaf is 0. then I can just define H upper star of S as H upper star of gamma S upper star. What does this mean? Well, this means I forget S, and I keep the sequence of S naught, S1, etc. Then I apply the functor gamma, which is basically taking sections. And then I get a sequence of abelian groups or modules over some ring, and the sequence will be complex. It will not be, in general, exact anymore. It will be complex. And so I take the cohomology, and this is the cohomology of X. Now, the important thing here, I can take any sort of gamma cyclic sheaves as S0, S1, etc. Injective will do, flabby will do, and in particular, fine sheaves will do. Now, what is a fine sheaf?
Excuse me, gamma is
Global sections.
global sections.
Now, what is a fine sheaf? A fine sheaf, well, a sheaf is fine if and only if its endomorphism sheaf is soft. Now, which is not particularly helpful because what's a soft sheaf? A soft sheaf is a sheaf such that every section extends, every section over a closed subset extends to the whole to the whole space. So, in particular, fine sheaves are soft, but soft sheaves are not necessarily fine, although there aren't any natural examples. In algebraic geometry, there aren't any soft sheaves. There are only injective sheaves, and this is it. In topology, there are plenty of examples of soft sheaves, and in particular, the sheaf of smooth sections. The sheaf of smooth functions on a smooth manifold is fine, so it's soft, and also the sheaf of continuous functions on a sensible topological space. Normal probably would do, is also soft and fine. Anyway, a fine sheaf of rings is, a soft sheaf of rings is automatically fine. The good thing about fine sheaves is a fine sheaf tensor anything is fine. So if and every module over a fine sheaf is a fine sheaf. So basically, all these sheaves when I take when I sheafify the sections of any vector bundle, not necessarily lambda 0 q, any vector bundle. If I sheafify smooth sections of any vector bundle, I get a fine sheaf, which means it's good for calculating the cohomology. Now there is another thing which we need here, and it's the D-bar Poincaré lemma. And let's talk about it after the break. So, say again?
Is it true that these shapes are solved?
Well, technically this is a vector bundle. Then I want to construct a sheaf.
We take the infinity section.
Yes, then I take C infinity sections, then I sheafify. And yes, those sheaves are soft because they're fine, and they're fine because they're modules over C infinity of X. and C infinity of x, the sheaf of functions on x is fine.
How to say fine in Russian?
Тонкие. Вот пучки бывают мягкие, тонкие и белые. Вот почему такая терминология?
Я только мягкие.
Ну, сейчас бывают мягкие, вялые, тонкие и какие еще?
Иногда еще и плоскими называют.
Ну, плоские, да, значит, бывают еще плоские. Значит, какие еще? Значит, бывает... В общем, есть какой-то еще термин, я его просто сейчас забыл, но действительно, значит, пучкам не позавидуешь. Anyway, yes, so the point is, this is a vector bundle, this is a vector bundle, I take the product, I get a vector bundle. Then I take the infinite sections, then I sheaf a phi. And my claim is all resulting sheaves are good for calculating cohomology, meaning they're all gamma acyclic. And they're all gamma acyclic essentially because they're all modules of the sheaf of smooth functions, which is fine. Okay, I suggest we take a break for a minute or two or several, and okay, I'll turn this off. And how much time do we need? I don't know. Let's say let's take a break until 6:10. Okay. Так, значит, знаю, что запись лучше. Ну, можно поставить. Нет, можно поставить на паузу. Если можно поставить на паузу, но не выключать, я предлагаю поставить на паузу, но не выключать. Okay. Okay. Let's see. So we let me write down what I said at the end of the previous class. Firing sheaves are good for calculating cohomology on reasonably good spaces. Paracompact would do. Paracompact house. Suppose we have a smooth vector bundle on a smooth manifold. Then the sheafification of smooth sections of X is fine.
Wait, is it X or?
Well, U.
Why do we need to take sheafification?
Well, because otherwise we don't have a sheaf. We don't have a sheaf unless we sheafify.
You mean sheafify?
But yes, in this case we so in general this is a tray sheaf. But if I take this particular brace sheaf, it's a sheaf. So we don't really yes. Let's get rid of sheafification. Is a fine sheaf. But in general, not every brace sheaf is a sheaf. And an explanation why this sheaf is fine is that it's a module over a soft sheaf of rings. Okay, so as a result, sheafifying sections of these vector bundles results in soft sheaves. And let me erase this part. So, while I'm erasing, where is this all going? I want to explain why the sheaf cohomology of V. I'll explain shortly what this is. Is isomorphic to the cohomology of some elliptic complex. Okay, now
These are just examples of fine sheaves.
yes. So to we get a sequence of maps between sections of vector bundles. Now, this sequence of maps is clearly compatible with restricting to open subsets. Well, that's basically where we use one of the basic properties of a differential operator. To calculate the differential operator at a point, it suffices to know the values of the section we apply the operator to in an arbitrarily small neighborhood of the point. So when I sheafify, I get some number of sheaves and maps of sheaves between those. Going there's something which I want just to mention without going into more detail. Poincaré lemma. Well, first of all, let's try to remember the classical Poincaré lemma. The classical Poincaré lemma says that the de Rham cohomology of Rn is 0 except in degree 0, in which case it's R. Okay, but what's another way to state the same result? well, as a consequence of this result, we get the following thing. The sequence of sheaves is exact. Which sequence of sheaves? Well, the first one is the constant sheaf with stalk R. This is the sheaf we want to resolve. Then I take zero forms, in other words, functions, and sheafify. In other words, I consider the corresponding sheaf. And then I do the same with one forms and so on. So Poincaré's lemma implies that this this sequence of sheaves is exact. Now, does everyone agree? Well, I want to, if I want to check that it's exact, I only need to check that it's exact at near in a small neighborhood of every point of x, and then I apply the first I apply the definition. I take an element in some an element in of some of the cohomology sheaves. I suppose it's non-zero, and then and so on. Basically, it's not too hard to prove that this this sequence is exact. Now there is a similar statement, which is the D-bar Poincaré lemma. And this D-bar Poincaré lemma implies that the similar sequence of sheaves the similar sequence of sheaves is also exact. And the D-bar Poincaré lemma says that the D-bar cohomology of a polydisk is 0, except in degree 0, and in degree 0 it is basically the holomorphic functions on the polydisk. Okay, now And by the way, here the tensor product. The tensor product is oh dear. Hold on. No. First of all, what? No. Okay. So I'll start again. What is calligraphic E? It's the sheaf of sections of Broman E. Okay, and what is this? This could mean two things, but they are isomorphic. First, I could take this tensor, this, and it's a vector bundle, and then I could take sections. Or I can sheafify both and take the tensor product of the resulting sheaves as modules over C over the sheaf of C infinity functions, and the results are the same. Now. Oh yeah, yes, because 0, 0 is okay. 0, 0 is already here. Okay, let me write it like this: E, E, and then we get 0, 1, and so on.
I think it's not a constant sheaf over C. I think on left.
Okay. Oh yes. So sorry. No. You're right. Yes. So what we have here is x. A sheaf of holomorphic functions. Thank you. Yes, because otherwise we wouldn't be able to resolve the sheaf of holomorphic functions, which is basically the reason why we're doing all this. Okay, now.
When we take d bar of holomorphic functions, we obtain 0.
Yes, that's the whole point.
The first arrow is just an embedded. It's not a d-bar.
Okay.
No. Hold on. I have this map of sheaves, and then the kernel of this map is the map is d-bar, and then the embedding is one more step to the left. The kernel of d-bar is holomorphic functions. But this map is d-bar.
Okay, but then the vector should be correct. This one. There should be
Okay, sorry. So this is holomorphic. This is smooth. They're smooth functions. Okay, now E. Roman E is a vector bundle. So when we sheafify, we get actually a locally free module over C over the sheaf of functions on the sheaf of smooth functions on X. What does this mean? Well, this means for every small x inside capital X, there is a neighborhood such that the sections of E over this neighborhood is a direct sum of some number of copies of the smooth functions. Well, every free module is flat, this sheaf is flat over this sheaf. What's Volodya? What is a flat sheaf over some other sheaf? Aha. Okay. So suppose, well, to simplify, suppose I only want. No, I can't simplify. Okay. So suppose I have a sheaf of rings over some space. Now I want to and some other sheaf. I want to know when tensor product by this other sheaf over the sheaf of rings preserves exact sequences. The condition is very simple. All stalks must be flat. Is this notion familiar? Так, значит, Володь, так давайте я попробую быстро объяснить по-русски. Значит, есть пучок колец, и все пучки модуль над этим пучком колец. Значит, возникает вопрос. Вот, значит, у меня есть какой-то пучок, я хочу понять, когда умножение на этот пучок сохраняет точную последовательность. Значит, ответ такой, что очень простой. Значит, что все ростки вот этого пучка должны быть плоскими. Ну, это один из критериев. А что такое плоский модуль? Плоский модуль – это модуль, умножение на который сохраняет точность. То есть всякие там пучки-стручки здесь не важны. Значит, мы просто хотим вот тупо послойно посмотреть, вот если там все плоское, то тогда окей. Хорошо. Значит, но теперь давайте посмотрим на, значит, какой у нас пучок. У нас пучок гладких функций. Значит, какой у нас модуль? Ну, вот сечение вот этого пучка. Ну, давайте посмотрим, вот, на что происходит над маленькой окрестностью. Над маленькой окрестностью вот этот вот модуль, он просто распадется в прямую сумму. Ну, поэтому над маленькой окрестностью у нас уже на уровне предпучков, значит, вот это будет плоским, ну, просто прямой суммой вот это. Вот, но, значит, отсюда не очень сложно понять, что там на уровне ростков тоже будет плоское. Значит, поэтому вот это вот ш от е, она будет плоским вот это. Okay, so this is a flat module over this. So when I tensor everything by E, I get another exact sequence. Okay. Actually, I only want now. I only want this part. E C infinity lambda 0 0. E C infinity lambda 0 1, etc. So we get an exact sequence of flat sheaves, which is precisely, an exact sequence of fine sheaves, which is precisely the sequence we had on the right.
I think is a problem. OX is not a infinity module.
Well, yes, but we're coming to that.
Okay.
This is precisely anyway. We'll yes. Notice that it is not here. I did not include it here. So far, I know two things. I have this sequence of sheaves. It's a sequence of fine sheaves, and moreover, it's exact. What's the kernel? What's the kernel of what's the kernel of the first map? The kernel of the first map is precisely the sheaf of this time holomorphic sections of E. Now, does everyone agree? Well, let's look at this bit. Here we have the kernel equal to holomorphic functions on X, to the sheaf of holomorphic functions on X. Now, what happens when we multiply everything by E? And here I probably want to consider these to consider the vector bundles first and sheafify next. And then the whole locally the whole thing just splits as a number of copies of this sequence on the level of sheaves. So I don't need to worry about the fact that this is not a C infinity module. Let's see. Is there a better way to describe this? Let's think a little.
Can we say that E times my lambda 00 is OX module?
Yes. Well, they're all. Yes, they're all OX modules because E is. Anyway, the result we're interested in is that the kernel of this map of sheaves is actually something something interesting. Namely, it's the sheafification of the sheaf of holomorphic functions, and
I don't understand why. So these sheaves are the infinity of X modules, right?
but yes.
So the kernel is also the infinity of X module.
Okay, but hold on, but d bar is not infinitely linear.
Okay, so this sequence is a sequence of OX modules, or it's a sequence only of sheaves.
Well, it is a sequence of OX modules, but those modules aren't very nice. They're infinite of infinite rank and so on.
Okay, understand.
Okay, so we have reduced. Basically, we have constructed a fine resolution of this sheaf. What is this resolution? Well, it's this sequence of fine sheaves. And as a result, the cohomology of the sheaf of holomorphic sections is the same as hi of. This is important. I'll just write it properly on. At the top of the blackboard rather than at the bottom. So hi of sheaf is isomorphic to hi of this complex, basically. And while we're at it, let's also know that this is the same as hi of that if X and E are complex algebraic, not just analytic, then by Gaga the coherent cohomology of E is the same as the cohomology of this sheaf. Now, what's the coherent cohomology? Instead of holomorphic sections, we could take algebraic sections. And what we get is a module of the algebraic sheaf O of X. And then basically the same applies. We want to we have a sheaf over a sheaf of rings, and we calculate or define the cohomology groups, which in this case will be complex vector spaces. And if we assume Gaga, then and Gaga is a series of results which are mainly due to Jean-Pierre Serre, and the main idea is that if we have something compact, smooth algebraic, then algebraic and holomorphic sections, cohomology, vector bundles, and so on are essentially the same. And it's not at all true if we drop the assumption that X is compact. There are, for example, plenty of functions from C to C which are holomorphic and not algebraic. But over compact manifolds, this doesn't happen. Okay, now okay, so what have we done? We have reduced coherent cohomology to the cohomology of some complex, which is formed by spaces of sections of vector bundles. Now we want to see whether or not this is an elliptic complex. Now here there's some okay, let's Okay. This. Well, there's one thing we need to check to make sure this is an elliptic compass. We need to calculate the symbol of D. Sorry, the symbol of D bar, and we need to understand why the sequence of the symbols is exact. Let's first consider the case when there is no E. Then the symbol then the symbol is what? Let's recall the symbol of the usual Durand differential. Suppose I have a real manifold, smooth, and I have the Durand differential, which goes from P forms to P plus 1 forms. Now, what is the symbol of the Durand differential? It's wedging with psi. Well, here the same applies, but we have a decomposition of psi. Let's remember that psi lives in where does it live? It lives in the fiber of the cotangent bundle over X. Now, okay. The cotangent bundle, just like any vector space over C, goes to itself tensor C over R. Basically, an element psi goes to an element tensor 1. And then the this thing splits into 0, 1 and 1, 0 components. So I can write the image of psi as a sum of two components, 0, 1 and 1, 0. And so here I need to wedge by something. And what is this something? Is it the 0, 1 component or the 1, 0 component? Or something else entirely? Okay, and
We need to go from lambda 0 to lambda 0
this is a good argument. Although it's well, it's not rigorous, but yes, the idea is we want to increase this index rather than the other one, and so we multiply by we need to multiply by 0, 1. Okay, but how to prove it rigorously? Well, just remember that this is the usual de Rham operator, and the symbol of the de Rham operator is essentially the sum of both components. More precisely, the symbol of the complexified de Rham operator is the sum. And then we project, and which means only project onto which? Project onto the 0, 1 component, because we take d bar. D bar, blah blah blah. We here we apply the de Rham differential, just as usual, and then we only keep this component. And for q equals 0, we only keep the 0, 1 component. Okay, so we'll take this and forget all components apart from 0, 1. Okay. So, formally speaking, we have a composition of the de Rham operator, which is an operator of degree 1, and a projection, which is an operator of degree 0. And then we basically just can formally calculate the index of this. Okay. Now, sorry, not the index, the symbol. Okay, the symbol with the symbol with E is essentially the same, except that we tensor by the identity of E, which is more or less straightforward. Okay. Now the only thing we want to know is why the sequence of the symbols is exact. So let's do that, and then we'll basically run out of time. Not quite yet. No, we still have time. Anyway, so again, we want to know why the sequence of the symbols is exact. It suffices to prove this without without E. Why is it exact?
Because it was flat, so after transferring it got the exact again. No.
This time I have I'm interested in the sequence of vector spaces. Okay, let's write those down.
Currently the psi is not 0, but psi 01 is 0.
Well, it's precisely what we want to know. Let's see. Okay, so what? Which sequence is or isn't exact? Okay, suppose I have V. Suppose I have this vector space, and okay, so okay, what are these? These are yeah, I have C V bar, then okay, and all maps are wedging by wedging by psi 0, 1 for psi non-zero. Well, that's and the answer is this. This sequence is exact if and only if psi non-zero, psi 0, 1 is non-zero. Well, let's see. Well, actually, we know a formula for psi 0, 1. Which we saw an hour ago. what does this mean? Well, we want to have an element of the complexified vector space. So what's the formula? Well, I take psi, and then I consider I consider multiplication by I as a real operator. Apply it to psi, and then multiply by I, but in a different sense. And so this thing is not zero for psi non-zero, so the sequence is indeed exact. Okay, so the fruit of our labor is as follows. We have reduced calculating the cohomology of something complicated, namely the sheaf of holomorphic or algebraic sections, to something equally complicated but completely different, namely the cohomology of an elliptic complex. So, that's so. So there are two things which are important to us. Well, the first one I've already mentioned. We have an elliptic complex, and its cohomology are the cohomology groups of coherent sheaves. But the second is also important. The index of this operator is the Euler characteristic, and the Euler characteristic of as opposed to the whole cohomology, the Euler characteristic of a coherent sheaf is relatively easy to calculate. It's given by the Riemann-Roch formula, and the index formula gives the Riemann-Roch formula in this particular case. So, we'll calculate the exact expression later on, but as an advertisement, the Riemann-Roch formula for smooth compact algebraic varieties follows from the index formula. And then in algebraic geometry there are other versions of the Riemann-Roch, and but on the other hand, the analytic Riemann-Roch formula works for analytic varieties, analytic manifolds, which are as non-algebraic as it gets. Anyhow, does what I've just said make any sense?
So now we know the technology by the dimension.
We know that the cohomology vector spaces have finite dimension as long as we as long as we know that we have a fine resolution of the sheaf of holomorphic sections. And we need to know that this is an elliptic complex, because otherwise we don't know that these spaces are finite dimensional. For elliptic complexes, we know from 2 weeks ago that all kernels and co-kernels are finite dimensional, which is why and so on. So to calculate the index, we need the index theorem. So all the rest follows from the general theory of elliptic operators. But to deduce the Riemann-Roch theorem with an explicit formula, we need the index theorem. Assuming two theorems from 2 weeks ago, which I stated in the beginning of the class, but which we haven't proved yet.
So we know it's not for any complex manifold, right?
For every compact complex manifold, yes.
Doesn't need to be projected.
Or indeed algebraic. Okay. Now, I don't want to start something completely different because everyone's tired. But let's see if we have any questions, and if we want to review something which we have already done. In particular, is everyone familiar with Chern classes? Okay, let's solve some problem on Chern classes. Okay, suppose I have a smooth complex algebraic curve of degree d. We want to calculate the genus. Probably you know the formula, but how to prove this formula? What do you think?
basis in the space of holomorphic one forms on X.
Is it simple? I don't know. Maybe there is a simple way to do it, but it looks horribly complicated to me. Well, X is we don't assume that X is given by an explicit equation. X is just something, some curve. Well, for some particular curves, such as the Fermat curve, for example, which is given by x to the nth plus y to the nth plus z to the nth equals 0. So for the Fermat curve, there is a way, namely you could project it to CP1 and use the Riemann-Hurwitz formula. But let's not use it. Instead, let's calculate the Euler characteristic. Well, the Euler characteristic is the same as the Euler class evaluating the fundamental class. Now, does this make any sense whatsoever? Okay, so apart from the Chern classes, there is a very important class, the Euler class. How to define the Euler class? Well, basically, the easiest way to the easiest way would be to use the Thom isomorphism. Now, does everyone know what the Thom isomorphism is? Actually, we already mentioned it at some point last time. Okay, but no one remembers. Okay, let's review the Thom isomorphism. It's an important thing. Suppose I have a vector bundle. Let's denote its rank R. My claim is the vector bundle is orientable if and only if there exists a U inside HR. U inside HR of E modulo E naught, where E naught is the set of non-zero vectors in the total space of E, such that for every x and x, U restricted to EX, E naught X is a generator. A generator of what? A generator of H, R, EX, E naught X, which is the same as HR, RR, mod R, R minus 0. Okay, does this make any sense?
Is it H1 or HR?
HR. Okay, and if such an element exists, it's called the Tom class, and anyway, I encourage everyone to read about the Tom class and also the Euler class in the book by Characteristic Classes by Milner and Sashev. Okay, so the Tom class restricted to every couple, the fiber minus 0 should generate this cohomology group over Z. And to define the Euler class, we just take the Tom class and take it to the cohomology of does everyone understand what this where this map comes from?
Map from E to E modular E.
Yes, basically it's part of the long exact sequence of the couple E naught E. Okay, so the total space of E is a homotopic equivalent to X, so where this isomorphism. And under the composite, U goes to some element which would define to be the Euler class. Okay, the Euler class is very well. It's probably the most important characteristic class, and the Chern classes are only interesting because they sometimes allow one to calculate the Euler class, and the Euler class is it's some cohomology class. It's in general not invertible, for example, and the total Chern class is invertible. Okay. Anyway, let me continue here. So, for complex vector bundles, the Euler class is the same as the top Chern class. Okay, Tx is the tangent space. It's the tangent vector bundle. It's a complex vector bundle. So I can take here C1 dx evaluated at on the fundamental class. Okay, now what do I do with this? Well, I need to calculate the C1. How do I go about this? Yes, well, because C isn't very high dimensional. In fact, it has dimension 1. Say again?
The order characteristic of X, is that trivial? The order characteristic of X is the order class of...
Depends on how you define the order characteristic.
Oh, no, I mean, the order class and order characteristic would be some of the homologies, the random homologies. Order is some sort of random homology.
Yes.
So, is that trivial?
I don't know. You tell me.
Because I read the section of order characteristic on paper, but I didn't see this. He said to see the information in the order characteristic, go and see some references.
Well, this formula only makes sense for smooth manifolds, and for smooth manifolds, we could use two things. First of all, the Euler class is Poincare dual to the zero. To the zero locus of every section, and in particular, if this is true for every bundle over a smooth manifold. If we take the tangent bundle, then the zero locus of a section is just a collection of points. But these need to be taken with signs. It's a collection of oriented points. And then we use the theorem you already mentioned today, namely the index of the vector field, which is the same as the intersection of the vector field with the zero vector field. Is the same as the Euler characteristic calculated using using simplices. Okay, now we have this C1 of dx. So we have tx goes to tx, to cp2 restricted to x, and this goes to the normal bundle. And what's the normal bundle? Now, the x is a section of O of D. So the normal bundle the normal bundle is O of D.
Maybe something that
it's more general because it works for not necessarily for line bundles. It works for all bundles. If you have any vector bundle, maybe of an arbitrary rank, and take a smooth section, the normal bundle of the zero locus is the bundle itself restricted to the zero locus. So we basically get L of D restricted to X. Okay, now we let's take a positive generator of H2 of CP2. In other words, C is C1 of O of 1. Then C of O of D is the same as 1 plus dc. Another instance of bad notation, this C is not the same as this C. This C denotes the total Chern class, which means in our case 1 plus the first Chern class. Okay, so we know the Chern class of this bundle. Now we also know the Chern class of T CP2, and it's 1 plus C to the power 3. And 1 plus c to the power 3, which is the same 1 plus 2c plus 2c squared. Now, does this formula make any sense? In particular, why is it 3? Why isn't it 4? Or 5? Or 2?
It's the same way you calculate for each loading classes. You embed in one pair dimension.
Okay, we need to calculate the what? Let's calculate the tangent bundle of CPN. Okay, does anyone remember how to describe the tangent bundle of CPN in terms of some other bundles?
You only know the tangent space to a point of CPN. Can be identified with quotient of n+1 dimensional vector space by this by a line that is supposed to a point.
Well, let's it's home from somewhere to somewhere, but let's try to remember from where to where.
The categorical bundles is orthogonal factors.
I think it's from Q to gamma 1.
What is gamma 1?
Well, gamma 1 is the tautological bundle. Epsilon n+1 is the trivial n+1 bundle. Q is the quotient. Gamma 1, same as here. Okay. Now, so what do we get? We get 0, hom, gamma 1, gamma 1. Hom epsilon n+1 gamma 1 is CP in 0 Okay, so so home from
Can we check this Gorginov or CP1?
hold on. So this thing is no, it's probably no, it's probably the other way around. Why? Well, because yeah, it's probably the other way around because the answer is wrong. If I do it this way, the answer is wrong. I get gamma 1. Well, I'm supposed to get the dual of gamma 1. Okay, never mind. Gamma 1, Q. Okay, then what?
Okay, now it's better. It doesn't work for CP1.
Okay, so let's see where the sequence will go. So gamma 1 Q.
No. All right.
Gamma 1 Q. Gamma 1 epsilon n plus 1. So basically I take the sequence gamma 1 epsilon plus 1 q and apply hum from gamma 1 to this sequence. And yes, then the answer is C of t Cpn is 1 plus C to the n plus 1. Where C is C1 of hom gamma 1 epsilon 1, which is the same as C1 of O of 1. Okay, now the answer makes sense. Okay, does everyone agree? Follow? Okay, let's assume that this formula holds. It's in the book by Milner and Stashev somewhere. And then we
Just hold from Euler's sequence, right?
and what is Euler's sequence? Probably it is the Euler sequence.
Oh.
Anyway, there is a more general version of this for the for Grassmannians and so on. Anyway, for CPN we get this, and so basically we have the Chern class of this and also this bundles. And let's note that both Chern classes, in fact, come from CP2. They're both restrictions of something which is defined on CP2. Well, this is defined on CP2, and so is this, and then we basically what we need to do is first calculate the answer on CP2 and then evaluate the result on the fundamental class of X. Well, let's calculate the answer on CP2. On CP2, what do I have? I have one plus C cubed divided by 1 plus DC. Now, let's see whether or not this makes sense. Well, 1 plus C cubed does make sense. It's an element of the cohomology of CP2. But what is 1 plus DC? Well, it's another element of the cohomology of CP2. Now, let's see that we have a 1 here. And this means this element, which I have in the denominator, is invertible. In which sense? Well, in CP2, everything terminates in degree 2. So what do? I take 1 plus DC, and then I use the formula for the geometric progression. And normally, this could have gone up to infinity, but it stops in degree 2 because all the rest is 0. Okay, so then I need to restrict to the fundamental. And what do I get? Let's see. Well, first of all, the degree 0 part is clearly 1. Now, what do I get as the degree 1 part? Well, I have 3C, which comes from this product, and I also have minus DC, and plus etc. Okay, now I have 3C minus DC. What happens when I evaluate this thing on an X? Well, I only need to evaluate C on X. But X has degree D. So C evaluated on X is D. So I get 3D minus D squared.
How did you do that? Why would you replace C by D?
Well, C is the positive generator of the cohomology of CP2. What happens when I take this positive generator and evaluate it on the fundamental class of X? Yes, the positive generator is C1 of L of 1, and which is the same as the hyperplane section class. And in our case, hyperplane means line. So what does this class do? Basically, it counts the number of intersection points of X and a sufficiently general line. And the result is D. So C evaluated to the fundamental class is D, and basically we get this formula. And then, well, starting from the Euler characteristic, it's pretty straightforward to calculate the genus. And the genus is D minus 1, D minus 2 by 2. Okay, now it looks like everyone's tired, and well, no surprises there. So, are there any questions? Comments and so on. Well, if there aren't any questions, let's call today. And I would like to again encourage everyone to attempt problems on characteristic classes because we'll need those pretty soon. Okay. Let's see how it works.